Okay, here we are, second 105A video lecture, and got some stuff on the board already. Physics 105A video lecture number 2. So let's start with an announcement. Speaking of the homework, I want it to be turned in every Friday, and you're going to want to get some kind of app for your phone that turns pictures into PDFs if possible, because I definitely need something from you that's easy for me to print out. And I believe Adobe has a free app that'll turn a photo into a PDF, so let's keep that in mind. So yeah, we'll turn everything in on Friday, or whatever we have on Friday, we'll take it in, we'll turn it in. Next, I have a little thing about taking notes. Make sure you leave plenty of space in your notes, and then you can fill in with other acquired wisdom as we work through this. And for example, today I have a little clarification on the nonlinear friction law. I looked at what we had talked about, and there was more to be said, so I'll set something up like that. And then we'll move into the cycloid, got some interesting stuff there. And good, let's get started. So I can erase this here, and we'll start with the discussion of that nonlinear friction law that I had on the projectile with friction last time. Okay, here's what we had. We had, for our projectile, we were in X and Y standard, gravity was pointing down, and we had mass times acceleration was equal to, actually, G pointing down, plus a friction law. Okay. And the linear friction law it was just some constant friction opposing the velocity itself, proportional to the velocity opposing the direction of the velocity. And then I wrote for the nonlinear case, I said F would be minus K, some function of the magnitude times V. So let's be a little more explicit about this just to see what I was talking about. This is the vector. So an example, we had the quadratic friction law when we were working on this in one dimension. Okay, so we had F equals minus KV squared. How does that look when we're talking about a vector? I'll just put this parenthetical, that was our 1D case. One-dimensional case. Well, that looks like the following. F would be equal to minus K V squared, and then we would have the vector V divided by its magnitude. In other words, what I have in parentheses here is just a unit vector. Okay, so that's how we can say this is just a unit vector pointing backwards. So we have KV squared, and that's our law, our friction law. But look what happens here. If we write this out, we have minus K. I'm just going to do the X component. That'll actually be enough to see what's going on. Well, minus K X dot squared plus Y dot squared, right? That's V squared. And then we would have, we're looking at the X component, so it would be X dot divided by square root of X dot squared plus Y dot squared. Okay, this simplifies a bit. Simplifies, but it doesn't make it any better. Okay, what does it simplify to? For Fx equals minus K root X dot squared plus Y dot squared times X dot. Okay, I'll put this in a box here. A little bit smaller than it should turned out. Okay, those are x dot squared plus y dot squared. And f sub y would be the same thing, except it would have y dot here. Now you can see how this is really coupled. I'm going to go ahead, how these equations are coupled. I'm going to go ahead and write them out now in the form it would have been in our other problem. There's the result. Good. So this equation up here, I will write it out in the components, and this will be your comparison to what we are solving. We would end up with x dot equals minus k root x second derivative k over m plus y dot squared x dot minus g minus k over m root x dot squared plus y dot squared y dot. Okay, highly nonlinear coupled equations for which we don't have any kind of simple solution theory at all. Okay, good. So I wanted to, you could put that in your notes here or back where we were talking about that, where we actually have this differential equation written out explicitly now. You know, linear is nice. What we solved was just this, but now we've got that square root in there. It's a whole other can of worms opened up. Okay, good. So that, just to, like I said, add that to your notes. And good to go over just a little derivation I did here. I skipped some steps. You can go back to what we had done, make sure it all makes sense. Now let's say something about our cycloid. So the other problem I had talked about was supposed to result in a cycloid under, so the motion of the charged particle is going to result in a trajectory that is cycloidal. So the cycloidal trajectory of the charged particle. That's pretty much what we had ended with, dot, dot, dot. And I want to say a little bit about the cycloid because it's a good way to segue into our next topic. So we have x and y. We've studied the cycloid in the past. It is obtained by rolling a wheel forward, okay, and there's a little light on the wheel, and the light would trace out this path. Fine. So if the wheel has the radius r, we got here 2 pi r, and there was a parametrization of this curve, namely x was equal to r theta minus sine theta, y was equal to r 1 minus cos theta. I hope I got that right. And theta itself could be a function of a parameter if there was some dynamics going on. But this is just the parametrization in terms of the angle theta. When you roll out a full 2 pi, you've traced out that curve there. Okay, so we need to talk about parametrizations of a curve. And the length of a curve. Something you've done somewhere in one of your calculus classes, I'm sure. Parametrizations and then the length of a curve. So that's what we'll do next. That'll lead us on into important stuff for the dynamics in 3 dimensions. So parametrization, we've got the parametrization of the cycloid, and we're going to get the length of the cycloid next. That, in fact, that's going to be your homework problem as a nice concrete example. What is the length of a cycloid? That's interesting because you've got this 0 to 2 pi r here, but it turns out that this length, if you do the correct integration, it's a whole number. Who would have thought, right? This is a rational, and that's whole. This is irrational, and that's a whole number. Okay, so let's talk about the lengths of a curve. So if you have the parametrization of a curve, then you can obtain the length of a curve. So you've got some curve that goes here from A to B in space. Length of a curve, question mark. Technical term, it's called the rectification of the curve, which means to straighten something out. So rectification. You know, the way we obtain it isn't that bad. We can see that with a Riemann sum. Suppose you had a bunch of chords here, and you'd say we could approximate the length of this curve. L would be approximately the sum of all of these delta r's. We'll just sum up all the delta r's, and these r's are, you know, the endpoints of these respective vectors here. Each time you have a delta r, you take its absolute magnitude, you sum them up, and if you make this smaller and smaller, and the limit is Riemann sum, you're going to turn that into an integral, and you'll get the length of this smooth curve here. And therefore, you could say L approximately the sum of the magnitude of the delta r over delta tau times delta tau. So that's actually the same expression as this, except I multiplied and divided by a delta tau. Well, tau is the parameter, which is the parameter for the parametrization of this curve. And that's why if you let delta tau go to 0, this is going to turn into an integral of dr d tau magnitude d tau, and A and B are the endpoints of your parameter. So that's the length of a curve. R of tau is the parametrization, and just lest we forget, example, R equals R of theta for the cycloid. And what did our parameter run through? The parameter went from 0 to 2 pi, which is what I just had up there on the board a minute ago. So our homework is going to be find the length of the cycloid, calculate the length of the cycloid. Calculate the length of the cycloid. I'm going to keep setting this up for us, but this is your basic recipe or your basic development of the idea of the length of a curve. So we're going to do a couple more of these examples, and then we'll set up the cycloid again. Okay. Let's go ahead and do a couple of really trivial ones, and then we'll come back to the cycloid here, and you guys can take it away. Yeah. my really trivial example, the circle. Circle of radius r. Here we go. We're going to have the parametrization. And that parametrization is going to be r of theta is equal to r cos theta r sine theta. Okay, so I'm writing the vector as an ordered pair. And remember, I'm going to look for the integral of dr d theta, the magnitude d theta, and we're going from 0 to 2 pi. That's the actual definition of the general definition of the length of a curve where you have this parametrization. Well, let's even just take it right 2 pi. What is dr d theta? First of all, the vector, we'll say the magnitude of the vector dr d theta, which is minus r sine theta r cos theta, magnitude d theta. So the magnitude of that vector, generally we would do this calculation outside of the integral and then plug it in. Okay, but here we've got this right here. So the magnitude of this is the square root of the x component squared plus the y component squared. So minus r sine theta squared plus r cos theta squared theta. Okay, and of course sine squared is minus sine squared plus cosine squared is 1. We've got the square root of r squared is r, so we end up with r 0 to 2 pi d theta equals 2 pi r. Okay, I said it was a trivial case. I do the trivial ones, you guys do the hard ones. Okay. Yeah, but it has all the ingredients. So that was this ordered pair was the vector, that was its magnitude. The magnitude is the x component squared plus the y component squared, square root. Boom. Okay, so that's the example for a circle of radius r. Suppose we had a helix. I'll do a second example with a helix. Helix. Okay, for the helix, we have r equals, I'll use some different letters, a cos theta, b sine theta, no, not b, sorry about that, a sine theta, c times theta. Yeah, so what is this helix here? We're now x, y, z, and it's winding its way up. Okay, the helix right there. dr d theta vector would be minus a sine theta, a cos theta, c. And you know, I'll add this to the homework too, so you guys can just do it and get some practice. Okay, it's easy. It's an easy problem. You can see now. Then we're gonna, you know, how long is this helix? Well, you could go 0 to 10 pi, 20 pi, a million pi. We'll just go 0 to 2 pi. Integral 0 to 2 pi dr d theta magnitude d theta equals question mark. Okay, so let's put that on the homework as well. And then we can see how this cycloid is going to work, which is also the homework. Maybe I'll say another word about the cycloid. Okay, good. I'm going to erase this. This one, again, is pretty trivial. You're going to get sine squared, cosine squared is 1. And it'll be a constant again under the integral. Okay. Next. So now we want to do the same thing for the cycloid, and it'll be a non-trivial integral, but you'll figure it out. And yeah, so actually I've given you 2 examples. So for the cycloid, just to make sure it's up here neatly, the first step, you've got your R equals R of theta equals that ordered pair I just had on the board. And then we must have even done this. We did it in a different connection. Okay, dr d theta. No chain rule this time, by the way. No added chain rule. Dr d theta, you're going to get that ordered pair there. And then finally, you're going to have to figure out how to do this interesting integral. Once again, and the boundaries are important here. It's going to be from 0 to 2 pi. Magnitude of dr d theta. Remember, that's just the square root of the. Okay, dr d theta. Magnitude d theta. Same as the other 2 cases. This one's interesting. The answer is a whole number. And yeah, we need this practice with these parametrizations. So I've given you 2 trivial examples. You got the cycloid to work with, find out its length. And you can even review your notes and fill in how I got that formula in the first place with that little Riemann sum. Good, so what's next? What are we going to do with this here? So that's an end to that. So we have possibly enough homework for Friday now. We had those 2 problems from last time. We've got the length of the cycloid. If that's all, it won't be bad. Let's see what we have here next. Maybe add a little bit to this. Okay, next. Back to dynamics. Back to dynamics in 3 dimensions. Dynamics in 3 dimensions. So yeah, put Newton's law down there again. This is what we were doing when we ran into a problem that was going to deliver the cycloid to us. And our next major topic is going to be just like what we had in 1-dimensional case. What did we do in 1 dimension after we had gone through a bunch of examples of f of this, that, and the other? Okay. We went to the case where f is just a function of position alone. F is a function of position alone, and F being the force on our particle. So the case where F equals F of R. Right, the charged particle in the cross electric and magnetic fields was a force as a function of the position and the velocity. This time it's just the position alone. Well, recall mx second derivative equals f of x in 1 dimension. What did that give us? That gave us the possibility of introducing the potential energy and immediately having conservation of energy, which was really just the first integral of a 2nd order differential equation. So recall this here results in defining u of x eta x minus x prime dx prime, and 1/2 mx dot squared plus u of x equals e. So that's what we're going to do in 3 dimensions now. We're going to take a case where force is a function of position only, and then make our way down to conservation of energy. Very, very useful, of course. Yeah. Okay, let's okay. And we did this, we had a chain rule involved. You can look this up in your notes. Actually, we did this a few times, so I'm just going to go straight to working with this type of a force now. I'm tempted to just redo this derivation real quick. Yeah, in fact, I will. So let's just call this star here, star, proof of star. Just as a reminder, right? It's been so long, we've done so many other things. Proof of equation star here. Yeah, if we define this thing like so, we have dE dt, taking the time derivative of this, is equal to 1/2 m, and then we've got a derivative 2x dot, chain rule x second derivative, and then we have plus du dt, which is u prime of x, chain rule dx dt. Differentiate this, of course, is a 0, but hey, I'm trying to prove that, right? So 2's cancel, I have an x dot as a common factor, and I have m x second derivative plus u prime of x. And again, I'm supposed to be proving this. Well, this is Newton's law. Therefore, that's equal to 0. Okay, so that's the proof that if you have a potential energy of this form, if you have a force that's only a function of position, then you define a potential energy, you get conservation of energy. Okay, now we have to do the same thing with the 3-dimensional case. It's going to be more interesting, the more conditions put on this. So now the case, 3D case. Force equals a function of position. So what we're going to do is define u of r, it's vector position r, okay, u of r equals minus the integral f of r dotted into dr from some constant point A to r up here, so these are primed. So the argument is the upper boundary of the integral, and then first of all, this symbolically looks fine, but you have to define what you mean by this, okay? You have to define what you mean by this, and then you have to show that the derivative of u is actually equal to the function, the integrand here, at the upper boundary. Or you can just claim that you learned it in your math class and so you know it's true. But we'll do both. We'll claim we learned it in math and we know it's true, and we'll go ahead and prove it. Demonstrate it, first of all, say what it is we even mean by this integral. So what do we mean by this integral here? We're somewhere in space A, and here's our endpoint R, and we're integrating the, you could say it's the scalar product between f at various points and dr along some path here. So there's our path, we started here, taking this contour, ending up at R, the end point. And by the same construction as we had with our rectification, the length of a curve, we could do the same thing with little chords, except that for each little dr there, instead of its magnitude, we would be taking its dot product with the vector field that somehow lives here. You know, say we had a vector field like that. So we'd have a bunch of dot products, sum them up, we'd get that integral. Okay. So what you need is a parametrization and I'll call it R of tau, just to point out that this is not a dynamical equation itself. This is just a parameter that takes me from here to here. Parametrization R of tau. And then we can define integrals of this type. I'll go ahead and just do this one right here. Then this A to R f dot dr is defined as f, need more room as usual. We've got room. Okay. Let's move to the left here a tad bit. Yeah. Once more. So integral f dot dr a to r. So this is taking place in space. That's defined as f of r of tau dotted into dr d tau. Okay, so that's the force vector field. That's dr d tau, and then integrated with respect to tau. Okay. So you can see, cancel the taus there, it makes total sense. And then since you have a parametrization, you have to say this is from tau sub A to tau sub B. Any of our previous examples, it would have been that 0 to 2 pi. Okay. It would have been that 0 to 2 pi. So that's how that is how an integral like this is actually defined if you're going to do the integration. If you have to do the integration, well defined. So next, is this completely well defined? Well, there are some stipulations we have to make on this vector field for this to be reasonable definition. Namely, it has to be the value of this integral. Remember, this is just a point in space, r, so it doesn't matter how I get there, I have to always have the same value. So if this is one path, use another color here, and I have a second path like that, the yellow integral has to be the same as the white one. Okay, that's basically what it has to be. And then the proofs you got, the proofs you had in your math class or in earlier physics class would be that, well, if these are the same two values from this point, you know, A to R, then if I go by way of the yellow path and reverse the direction on this one, then the answer, then it should add up to 0. In other words, if u of r is the same value via the yellow and the white path, then if I go u of r here from A to R, and I go back on the white path from R to A, this is just going to reverse the value of this. It's going to get a minus sign in there, and I'll have u of r minus u of r equals 0, which is to say the condition for this to be well defined is that the integral along a closed path vanishes. Okay? That's our condition. So in so many words, integral closed path vanishes, and the condition for that is then a stipulation that we make regarding the vector field F. So let me summarize all that, because there's not that much room up here. I always like to leave something up here, so let's put this right in here. Okay. I'll just write this. I'll say this is well defined if integral f dot dr equals 0. So that little 0 here represents the closed path. And that's not the case for any old force. This requires that the curl of f equals 0. Okay. We're going to prove all these things, or at least sketch out the proof or indicate the proof, because this semester we're trying to prove everything we do. Yeah, so I'm going to leave it here for next time. I'm going to go ahead and erase this and just put a couple more things up here, and then we'll call it good. So yeah, the curl of f, this type of integration right here, we've landed in vector analysis, okay, vector calculus. So I'll just write here next some vector calculus and the integral theorems. The integral theorems. All right, this one here we're going to use Stokes's theorem, and we'll talk about all of them while we're at it. Okay, so the next thing we're going to do is some vector calculus and some integral theorems, and then after that, forces with a potential energy function. And that's going to take us into the central force problem finally, but we still have a little ways to go. Interesting stuff. And after that, the 1 over r potential. Okay, that's our plan. We had a bit of a homework discussion, so you have enough to do until Friday. And conceivably, I could add a little bit on Wednesday, still be due on Friday. But at least we have a good start on that. So we'll talk about integral theorems a bit and their relation to these integrals that we were just doing. And then we'll keep moving on through the dynamics. Okay, good. That's it.